think we'll start. We'll let people in as they come.
Okay.
So thank you for joining us today for the HGSN seminar. HGSN standing for High Throughput and Secure Networks. That's a challenge program led by NRC. Today we have the pleasure to have Lukas. We'll talk about quantum communication in free space optics. Lukas is a PhD student at the University of Ottawa with Professor Karimi. Maybe it didn't work in the previous seminars, but if there are people working in that field of quantum com and wish to present really briefly, like one slide or 2 minutes, their work or their company, please don't be shy, and we'll keep some time available at the end to do so if you wish. So I think let's start. Lukas, the floor is yours.
Okay. Thanks for having me, everyone. Thanks for coming. So, yeah, like Boris said, I'm a PhD student with Ibrahim Karimi at the University of Ottawa, and I'm going to present some work from mostly our research group regarding high-dimensional quantum communications in free space. So I wanted to start off with a little bit about me. I'm sure nobody really knows who I am. Some things about me. I'm currently training for a marathon. I recently started running. I do things like collect and have a bunch of houseplants at home. My friends and family say it's too much, but I don't have an outside space. It's like my garden. I do like hobbyist electronic stuff in projects. I have a 3D printer, an oscilloscope, and all the tools of the trade. Mostly, though, the 3D printer ends up getting used right now for making plant pots. And also, I'm interested, when I'm not reading about physics, I'm reading about Greek and Roman history. And this is actually why I started running. The marathon I'm going to do is the Athens Marathon, from Marathon to Athens. So my interests are feeding my other interests. I grew up in Windsor in the south of Ontario. I moved to Hamilton to do a Bachelor of Engineering at McMaster University. I first became interested in quantum information during a course on introductory quantum information in my undergrad there. And I was really interested in quantum teleportation and quantum communications because how unintuitive they were, but how kind of beautiful the results were as they came out. And so this interest, I pursued it, and I got in touch with Dr. Karimi at the University of Ottawa. And now my research focuses on quantum key distribution, particularly in free space up here in Ottawa. And so a little bit of table of contents for the rest of the scientific stuff that I'm going to present. I'm kind of going to go briefly over what is quantum key distribution, what does it mean to do high dimensional quantum key distribution. I'm going to go over a bit of earlier works from our research group with Dr. Karimi. And then I'm going to give some background on the information, or some background on the source of the errors in those previous experiments that were done. And then I'm going to finally talk about the work that we've been doing to predict and correct for these errors in free space communications. So starting off very high level, what is quantum key distribution? This is the big topic that I am researching. And so the most important things to know are that conventional encryption algorithms are susceptible to being cracked by a real-world quantum computer with sufficient number of qubits. And the only way right now that we know of to have information theoretically secure encryption is by using a random one-time pad that you encrypt your data with. And quantum key distribution is a way to distribute such a one-time pad between two parties. And using quantum key distribution, you can know with certainty whether or not somebody intercepted the key as it was being generated. And to do this, you need to encode information onto a single quantum particle. For our purposes, it's always a photon because they travel naturally. And this is mostly done in polarization because the technology is mature and it's like a well-known thing. And so the steps for quantum key distribution, first, Alice has in this table here on the left, you can see Alice has a random string of bits that she wants to use as a key for communications with Bob. She randomly must choose between one of two bases that are mutually unbiased to one another. And that means, if you look here on the right, if I am encoding information, for example, in vertical or horizontal polarization, and then I measure in vertical or horizontal polarization, I will know what was encoded originally. What it means for two bases to be mutually unbiased is that if I am encoding in this one basis, and then I measure in the opposite basis, there's no information that can be gained. So all of the information is lost. And this is really the core tenet of quantum key distribution. So Alice encodes her bit of information on the polarization in the chosen basis and sends that photon on to Bob. Bob randomly chooses one of those bases to measure in, and Bob records that measurement. After this, after a string of measurements has happened, Alice and Bob publicly discuss which bases they chose and throw away every instance where they chose opposite bases. Hypothetically, if you had no errors in your system and there's no eavesdropper, you'll then have a secure string that you can use as an encryption key. But if there's an eavesdropper, the eavesdropper must also do this basis measurement choice, introducing error in the system. And so by monitoring the amount of errors in your channel, you're able to ensure that nobody was eavesdropping on the distribution of this key. And so this is obviously, like I said, most often done with polarization, because this is a mature and simple technology that people really know how to work with. But photons aren't limited to polarization. There's other degrees of freedom that photons have that you can encode information in. Some examples I have here. So first, polarization. And then there's orbital angular momentum of a photon, which is a discrete value. It's just like orbital angular momentum of a particle, but it's the equivalent value for photon. You can encode information in the position or momentum of the photon, which is the k vector here in the bottom right. And really, you can encode information in any spatial mode of the photon. And so we're not just limited to polarization. We're very interested in using orbital angular momentum in our lab. And this is when a photon or a beam of light has a phase pattern that isn't flat Gaussian, but it's actually twisted. And so the phase of the light rotates as it propagates forward. And there is an associated quantum number, L, and if the quantum number is negative, there will be a counterclockwise, I think, twist, and vice versa for positive. And the number of twists per wavelength is the magnitude of the value. And so this is an infinite dimensional degree of freedom that you could choose to encode information in. And these vortices of the phase are actually robust in propagation, making for a theoretically very good way to encode information. And so, of course, we can do quantum key distribution instead of polarization. We can do it with orbital angular momentum. We get a photon with orbital angular momentum of -1 and +1 and replace the horizontal and vertical polarizations with those. And there's an equivalent to just adding them and subtracting them in the orbital angular momentum space. So we can do it. But one of the questions that kind of could arise is, why would we do this? And the main reason we would really want to do this is because, like I said, polarization is limited to 2 dimensions. But orbital angular momentum goes from -infinity to +infinity. And so instead of encoding just 0 or just 1 on these single photons, we can start thinking about encoding on 1, 1 or 1, 0 or more bits. And so we can start to encode more than 1 bit of information per photon that's sent across the channel. And this is awesome. This is a very clear result. Of course, you can, if I have an infinite dimensional space, I can encode more than 1 bit of information. But not so intuitively when you do the security proofs for quantum key distribution using high dimensional states like this. You are actually able to tolerate more errors in the channel. And so here on the left, I've plotted the key rate, which is actually the bits of information per photon. And you can see if with no errors, it kind of goes like you would expect. In 4 dimensions, I can have 0, 0, 0, 0, 1, 1, 0, and 1, 1. So that's 2 bits of information. And it increases every time you double because you gain 1 more bit of information. But as the error rate of your channel increases, with higher dimensional states, you're able to tolerate more errors. And so the idea, basically the reason that you would want to do it is to be in this regime where you're getting more than 1 informational bit per photon. But it's also interesting to be in this regime where 2-dimensional quantum key distribution wouldn't be possible, but you're able to do it with higher dimensional states. And so you really want to get above this 1 bit per photon. And so I think that I'm confident in saying that there's very little debate within the quantum networks community that future quantum networks are going to have to be multimodal, which means for sure we have fiber-based links, and that's a very important component, but we're also going to need satellite links, and most likely also ground-to-ground links for temporary locations that you're just needing secure communications for a period of time, or somewhere where you need to increase capacity rapidly, you might want to drop a link. And so for sure, free space is an interesting place to investigate performing quantum key distribution. And of course, high dimensional quantum key distribution if you want to encode more information. And so this is what our group has been doing mostly in the quantum communication space. So we've been doing free space experiments for a while, and we're looking to push the limits of high dimensional quantum key distribution. In 2017, our group performed a free space experiment between 2 buildings on the U Ottawa campus, and these buildings are 300 meters apart. They used OAM, but they also mixed in polarization to it. And this is a quick video. If you guys are from Ottawa, I think maybe we have some people from Ottawa. You can get a physical sense of like how far away this is. And if you know the University of Ottawa campus, maybe you'll know these buildings or the buildings around them. And so this was kind of a first of its kind experiments to be done. And in this experiment, they succeeded in being able to do quantum key distribution in 4 dimensions. And I placed this result on the plot that I showed you earlier. So while they weren't in this moment able to break that 1 bit per photon that we're shooting for, the main goal, they did actually tolerate an error that was just, you can't see it very well on the plot, but it's just greater than that 2-dimensional system would have been able to tolerate. So it's a great result, and people in the field like this one a lot. It was really one of the first of the kind. And after this, somebody had the idea to go underwater because the errors in the channel, they wanted to see, what happens if we go underwater. This might be interesting if you want to have a submarine that can communicate securely. But they set up an optical link in a pool, just 3 meters only, and they wanted to see, can it even be done? Was really the main goal. Like what happens? This wasn't something that had really been investigated to my knowledge at the time. And so when they did it, they found that the errors were almost immediately overpowering. In dimension 2, using OAM, they were able to do quantum key distribution with 0.3 bits per photon. But when they moved up to dimension 3, because of the addition of this extra mode, this extra optical mode, a third one, the error rate actually increased. And so even though they were doing high dimensional quantum key distribution, the information density of the channel wasn't actually increased. And by the time they got to 4 dimensions, the error was so far beyond what is tolerable for a quantum key distribution protocol that no information, this would have been an insecure channel in 4 dimensions. So interestingly, we can see the 3-meter channel in water was worse than that 300-meter channel for air. I placed it on that same graph for better. So it had less information capacity in the situations where they were able to do quantum key distribution and perform secure communications across the channel. But even still, it's valuable knowledge for future researchers. And I know there are teams in Germany and elsewhere still investigating, underwater quantum key distribution. There's people who are interested in this still. And so this is some background of what our research group has done in the past. And I showed this slide already, but I got to tell you guys that this slide is actually a really optimistic diagram of what a free space channel might look like. Here I have the moon, but realistically, the atmosphere is not so still like this. And this is a more realistic depiction of what would happen if you're doing free space communications, particularly in the day. Free space channels that you're operating in is the atmosphere, of course, and that's a fluid. It's not a vacuum. And this fluid moves around and causes errors, and it distorts your signal. And this introduces problems for ground-based channels, of course, and especially for satellite links, because you have to shoot your beam through the entirety of the atmosphere. And so here's a video of a building. I'm standing on the one side taking this video, and this is a building 5 kilometers away, taken through a telescope. You can see in the video, you can kind of make out there's turbulent eddies that are caused by atmospheric parameters like temperature and pressure. And these create small lensing, brief lensing effects throughout the channel. And for orbital angular momentum, this is actually or a really large issue, of course, because the information is encoded in the transverse phase profile. And so as they propagate, there are these small lenses that might take up some of the beam or the whole beam and distort the phase profile of the beam, which is where the information is encoded. And so the main takeaway here that I think is really important is free space is not free, which is why I have it underlined. When I zoom in, I think it really emphasizes the effects of the turbulence. This is a stabilized video. So I went in software and stabilized the video. So this is really, these ripples are from the turbulence. And that beige object, kind of in the middle there, is a shed that we have installed at the top of a building. And the shed's probably 8 feet tall. That black square on the left side of the shed is a window. And that window is probably 1.5 feet by 1.5 feet. And so our beam, if we want to shoot a beam of light out of that window and receive it 5 kilometers away where I'm standing in this video, taking the video, that beam is going to be very distorted by the time it gets there. It's going to be smaller than the window, of course, because it has to go through the window, but it's going to have distortions of the same scale. You can see the window moving, changing shapes. So this is a really large problem for free space experiments. And so this turbulence, there's many ways that you can quantify it if you're looking to do that. But one of the most popular and widely accepted ways is to look at what is called the structure parameter of the atmosphere, which is known as CN squared. It's the average variance of the refractive index over your whole path. So it takes the turbulence and kind of compresses it down into one number that is, I'm sorry, I think my headphones just died. Can somebody say something? Sorry.
Yeah, we can hear you.
Okay, okay, thank you. So the CN squared compresses the strength of your turbulence down into one kind of understandable number, and it averages over the whole channel. And a device that you can get to measure this is something called a scintillometer, and it shoots light over the channel and measures the variance of the intensity at the arrival point to calculate the structure parameter, or the CN squared, over your channel. And so we didn't put that shed on the roof for fun, right? We're trying to develop a free space channel for experiments in Ottawa. And so we bought a scintillometer because this is an important piece of equipment. We would like to know the turbulence conditions over our free space link. These two buildings that we have put sheds on are 5.4 kilometers away from each other, and we put our scintillometer, the one component on the one side and the other on the other. And we have an optical path that's not so traditional. It really goes over a lot of different things. And this is something that makes it really hard to model or kind of predict what's going on in the path. And so here is a video that I made to kind of demonstrate our optical path. I start really far zoomed out. If you don't know where Ottawa is, this is where Ottawa is. And so on the left side is our shed on the University of Ottawa campus. It's placed on the top of this building, which is Colonel By building on U Ottawa campus. And you can see the shed even in Google Earth. It's fun. As we go down the optical path, you can see there's a football field, and then we cross over the, I think, Rideau River. We cross over a bunch of houses, trees. We go very close to a building. We go over a parking lot and a complex. And this is the M55 library at NRC Montreal Road campus, where we have our other shed. And so this video is kind of to show you guys the scale of what we're working with here. This is very difficult to send beams back and forth, specifically OAM, and measure, do experiments on. And turbulence is a real problem over this channel. This channel is where that previous video of the shed scintillating came from. And so we installed our scintillometer across this channel, and we've been measuring the CN squared for quite a while now. So here's like a sample of data. And we got this because we wanted to correlate, results of our experiments to the turbulence at the time, so we could know how well we're performing in different conditions. But we realized we installed it and we let it sit there collecting data, and so now we have all this data. We want to learn other things from this data. We don't want to just use it as a tool at the time of our experiments. So what are some things that we can learn from this turbulence data in our channel? First thing that was super clear is that there's different regimes of seasonality. These don't exactly correspond with traditional summer and winter, but we called them that because they mostly line up. We noticed that in the summer, the behavior is very consistent, doing one thing. In the winter, it's not so consistent. And so here's a zoom in on a sample period of days in both the summer above and then the winter, quote unquote, below. In the summer, we have regular peaks of high turbulence in the day with a little bit less intense turbulence at the night, whereas in the winter, there's far less regularity. The average turbulence strength is definitely lower overall in general, but you get a lot less predictability. And even you get moments where you completely lose line of sight because it's snowing or it's a super cloudy or foggy day. This happens often in the winter. And something that's not so intuitive, I don't think, is that the lowest turbulence moments actually happen near sunrise and sunset. I would think initially at night would be the best time. But turbulence is actually caused by gradients in the temperature and the pressure and other atmospheric parameters. And so in the day, you have heat radiating in from the sun and going to the Earth. So there's a gradient kind of coming in to the Earth. But at night, it's reversed. And so the heat and infrared is being emitted back out, and the Earth is cooling down. And so since there's like a time where the gradient is going in and a gradient going out, there must be a moment where there's no heat or no gradient, essentially. And these moments happen close to sunrise and sunset. So that's something that we learned. And so now we want to really use this for something. We use this data. So we did some simulations to see what kind of success would we have if we want to do our QKD experiments over this channel, like the ones done previously. And we wanted to be optimistic, and so we said, what is the regime based on simulations that we would be able to do an 8-dimensional quantum key distribution protocol over this channel? And that region where it would be possible, and we could do it, is represented by the gray region of our graph. So for sure, winter is the time to do it. And of course, nighttime is the time to do it, not only because the turbulence is low, but also because the single photons, we're using single photons, so we want it to be as dark as possible. And so here's a 1-day period of turbulence strength data. And imagine this. I'm working in the lab, maybe 9 to 5 or maybe 10 to 6, expecting to go on the roof. The turbulence is going, it hits 6 p.m. And it's 6 p.m. I want to know, should I go on the roof tonight and should I perform experiments? Or should I go home and get a good night's sleep and save my energy for working in the lab tomorrow? And so this is real data that we collected. At night, the turbulence did not go into a region where we could have done quantum key distribution. So if I had gone on the roof that night and I tried to perform experiments, it would have been a failure, and we would have just struggled all night and had real difficulties. So that's March 7th. March 8th, let's do the same thing. it's the daytime, say I work until 6 p.m., and now I'm saying, should I go home and get some sleep, or should I stay and go on the roof? What should I do? I want to know at 6 p.m. As it turns out, March 8th actually would have been a really good time to go. We would have been able to do quantum key distribution experiments that the day before we couldn't have done. But the days, it don't make that so clear. So in the daytime, it's really hard to know what's going to happen in the future. But that's really what we wanted, because we don't want to waste our time going on the roof and doing experiments when it's impossible. So what we did was, first we tried to see if there are patterns in the data that are very easily recognizable, and we couldn't find anything super clear. And so we developed a neural network-based technique. It's based on a gated recurrent unit network, and it's particularly suited to time series data because the previous data points are also used as inputs for the subsequent data points. And we're inputting our turbulence data from the previous 12 hours. We're inputting relative humidity for the previous 12 hours, the solar radiation of the previous 12 hours, temperature, the time. So we're putting a bunch of weather parameters in to this network, and we're looking to get a forecast of over the next 6 hours, what is going to happen with the turbulence conditions. And interesting to note is that our weather station is not actually ours. We're getting the data from Government of Canada Meteorological Service, which is stationed 5 kilometers away. So if it works, that's really interesting. And here is an example of some of the predictions from the network. So the blue line that we have is the predictions of our neural network. We call it tarocco. It means tarot card in Italian. And the diamonds on this plot are the actual measurements from our scintillometer. So the more yellow they are, the lower the error, and the more green or blue they are, the higher the error between the predictions and the results. Our model, we found, can predict very well the upcoming turbulence conditions, at least during this period of time, based on the previous conditions. And we did predictions with 6 hours out, and we went up to 12 hours out, but we found that the results weren't as convincing for 12 hours prediction. But here are those 2 days that I showed you in the video. This is what our network predicted for the turbulence of those days. So if we had actually been looking to go on the roof there, we looked at 6 p.m., hey, tarocco, what's happening later tonight? Should I go? It would have successfully told us, yes, go on March 8th. No, don't go on March 7th. But I have to be honest, of course, I want to show you guys everything. And it doesn't work in every situation. In particular, the transition period from summer to winter, the network has very hard time predicting the turbulence. We believe that it's because of the change of seasons. The regularity in winter is less, but during the change of seasons, it will sometimes flip between summer and winter conditions. And we're hoping that the more data we collect, we'll be able to have multiple years of kind of fall situation, and the model will be able to improve. And so this is kind of the work that we did for turbulence predictions, and we hope that a more developed system might be able to inform a future quantum network of what will happen in the future. Here I have a random network example. And so it could inform users or network operators of link outages or give warning of upcoming bandwidth restrictions. So we really hope that our goal right now is that it might be useful for the upcoming satellite quantum satellite missions. So we can use our model to predict or inform the ground stations whether or not they should be the ones to connect with the satellite on a certain pass. If there's 2 stations nearby, but one has or is going to have worse turbulence conditions, they shouldn't be the ones to get that satellite pass. So that's our goal. And that's that work. But atmospheric turbulence is really, it's not a new phenomenon. Ever since astronomers invented the telescope, they've been kind of dealing with this. In astronomy, it's known as astronomical seeing. And on the right, I'm showing a figure from an astronomer in the UK. And it's subsequent pictures taken through their telescope of the star Sirius. And because of the atmospheric turbulence, you get to see a bunch of chromatic aberration. So this is something that people know very well. And here's another example from an astronomer in the US that took photos of Jupiter through his telescope on different nights. On December 6th, Jupiter is super clear. So the atmospheric seeing is very good. That means low turbulence. As opposed to December 11th, where the atmospheric seeing was really not so good. Of course, you can wait for a better night to take better pictures or do better quantum experiments, but that doesn't really work. So we've covered predicting upcoming turbulence conditions, but we want to be able to correct for atmospheric turbulence as well. And this is kind of where adaptive optics steps in. Adaptive optics is a technique to correct for turbulence as it's happening. And any form of active corrective system can be considered adaptive optics. But when most people talk about adaptive optics, you can be talking about a tip-tilt corrective mirror, but most of the time people are talking about something more advanced. And so here's with a deformable mirror that can correct more than just tip-tilt, but other aberrations. So here's a rough outline of what a modern adaptive optics system looks like mostly. We have an adaptive optics system in our lab, and this is the model this is a high-level overview of what it is. Incoming light, you have what you want to image, or for our example, it would be the signal for our single photons. And you also have to have a reference beam traveling through that has a known phase profile. That light bounces off of a deformable mirror or a corrective element, and then is detected by a sensor that detects the phase of the reference beam. And the phase is supposed to be a known quantity going in. So the difference between the expected phase and the measured phase gets calculated by the computer, which then closed loop controls the deformable mirror to perform live corrections. And for our adaptive optics system, these are some videos this is a video by the company that manufactures it. This is a Shack-Hartman wavefront sensor, which is built of an array of micro lenses that point by point measures the momentum of the incoming reference beam. And this generates an approximation of the incoming wavefront, and therefore the distortions caused by atmospheric turbulence of the known reference beam. And really importantly, the detection, calculation, and correction that you do, so this device needs to operate about 1 order of magnitude faster than the structure of the turbulence changing. So that typically looks like you need to operate on kilohertz scale. And this is the corrective element for our adaptive optics system in particular. It's a deformable mirror made up of piezoelectric micro pistons, and it can modulate rapidly. There's 97 in the specific mirror that we have. And this one can operate at 3 kilohertz, which is the range that you need generally for correcting for general atmospheric turbulence. And so we bought this system, but before we bring this onto the roof and we do experiments with it, we really wanted to put it through its paces, make sure it works for our purposes. So we set up a small turbulence cell in our lab with a hot plate, and the turbulence is totally uncontrolled, right? We turn it on and we set it to a temperature, but it happens naturally. The vortices and the turbulence cells are generated like naturally through the heat coming off this hot plate. And we send a reference Gaussian beam through along with our signal, which is a beam carrying OAM, through our channel. We correct it with adaptive optics, and then we measure the OAM to see if the error in the channel is sufficiently low that we could be doing quantum communications in the channel. So here is an example of the adaptive optics active and inactive in our channel. On the right, the adaptive optics is working, and you can really make out that it doesn't fix 100% of the problems. There's still fluctuations, but it maintains the original shape of the beam much better than without the adaptive optics. There's far larger variations in the beam shape when the adaptive optics is inactive. And so we're mostly interested in sending orbital angular momentum through, but of course, if you're doing polarization quantum key distribution or time-bin quantum key distribution, you're going to end up sending a Gaussian beam, or your photons will have a Gaussian phase profile. And so we wanted to see, how does this work with a Gaussian beam, and then it goes on our through the turbulence on our adaptive optics system and coupling it into a single mode fiber where we could then do a measurement. And we found a 2 times improvement in the amount of light detected based on a Gaussian beam going through, with adaptive optics as compared to without. And this would double the throughput of a polarization quantum key distribution system, because you would be losing half the photons if you use the adaptive optics. Or that's not the right way to phrase it, sorry. you would lose far less photons if you use the adaptive optics system. So this is promising to start for sure. And then we put the types of modes that you would use in an orbital angular momentum protocol through the system. So without adaptive optics, here on the left, this is the error rate. The gray region now is where we cannot perform quantum key distribution. So we can perform quantum key distribution if the error is under this gray line. And so without adaptive optics, we could not in any dimension do quantum key distribution. The channel was far too noisy and it simply was not possible. But when we started implementing and activating our adaptive optics system, we were able to get up to dimension 8, where by the 10th dimension, it fell through and we weren't able to go further. But this is really good. And it indicates that our system is going to be working for us on the roof, and also that future researchers or companies that are looking to do quantum key distribution should probably look into getting and implementing an adaptive optics system of their own, especially for high dimensional stuff. Oh, sorry. Okay, so in this experiment, in our lab scale channel, we are able to break that 1 bit per photon barrier. We have this dot here that was about I think 1.15 bits per photon. And we got to a relatively high number of dimensions, 8 dimensions, which was pretty good, especially for going through a really noisy channel. And here they are on the plot. And I want to really draw your attention, though, to something on the left plot. We have the 1 basis, which is represented by the circles, and the blue is without adaptive optics. So notice that the circle, the basis represented by circles here, is worse affected by the turbulence, but when the adaptive optics is activated, it's actually better corrected by the turbulence, as opposed to that secondary basis, which is less affected by the turbulence, but is worse corrected by the adaptive optics. And so why is this? We concluded kind of that the logical basis, which is just orbital angular momentum modes, has really widespread modes. And these modes cover our mirror really well, which means that they are able to get a large number of those pistons in the back of the mirror acting as corrective elements. So more of the pistons can correct more of the beam. But this goes hand in hand with the fact that it was worse affected by turbulence. And so it's going to pass through the turbulence and it's hitting more of the turbulence as it propagates. Compare that with that second basis here. This one is the one that was performed better in turbulence, but was worse corrected by adaptive optics. It has its intensity mostly concentrated in these lobes. And so only a few pistons on our mirror are going to be able to perform any corrective abilities. So we're not able to perform really high order corrections on these modes. And this kind of activated a question for us. Can we design a secondary basis that uses our adaptive optics system optimally, and we can still do quantum key distribution? And from my experience working with the system, I thought of these modes, which are orthogonal to each other, and I actually use them typically to calibrate our setup. And these are a superposition of 2 of the orbital angular momentum modes with the same number of vortices, but in opposite directions. And we had the setup all ready to go, so I tested it out immediately, and the hypothesis was good. They did perform just like the orbital angular momentum modes. You can see here, the error is the same, and it's much better than the angular modes, the other ones that we were using. But the modes are not fully mutually unbiased. At the beginning, I explained that it's important that these modes are mutually unbiased. So we called these, because of their non-mutually unbiased nature, we called them partially unbiased. And I did the experiment, but because it was easy and ready to go, but the thing that we really needed to see was, okay, we have to do the math now. Can we even do quantum key distribution with these modes? And that was a much harder thing to do. But eventually we came through. The math is hard, but eventually we got it. It came back, and these modes are not generally secure for quantum key distribution. If there is any amount of error in the channel, you could not guarantee secure communications. So these are no good. But something about this basis kind of really stuck out with us. These modes are in the form of qubits. They look like qubits, not like qdits. But you can do high dimensional information exchange with them. And so qubits are generally easier to manipulate than qubits, which have high dimension information. And that opened a new question for us. Can we make a high dimensional quantum key distribution protocol using states that look like qubits? And so this was our next thing. We, instead of only using two of the modes that were opposite in magnitude, we opened up the basis to be a lot larger, and we called these Fourier qubits. Each of them has two modes from the other basis with a relative phase between those modes. And we use this set of states as a secondary basis instead of the mutually unbiased one to basically reconstruct what would have happened in the original mutually unbiased basis. And this guarantees security. It looks exactly like a standard quantum key distribution, but you measure with different states and do math in the background. And like I said, it's generally easier to control qubits as compared to qubits. So this could, this technique, this protocol could kind of reduce experimental complexity for high-dimensional quantum key distribution protocols. So it's interesting. But one of the real main drawbacks here is that the total number of modes that you need to measure and monitor has drastically increased. It's a factor of d squared more modes. So as you get to higher dimensions, maybe this wouldn't be the way to go. And we tested these modes with OAM. This is what they look like. We tested this with adaptive optics, but even though that was kind of the source of our inspiration, they didn't perform any better with adaptive optics than the normal ones. And I really want to point out that the original partially unbiased basis states that were the inspiration are contained within this set of Fourier qubits, the Fourier qubit basis. And so while they didn't work on their own, they are an integral part of the new quantum key distribution protocol that we have made here. And we hope that this protocol that we created will kind of open the door for other high-dimensional qubit-like protocols. There was one previously, but it used the high dimensionality. It's called SHA-15. It uses the high dimensionality to enhance the error like tolerance of the protocol, but still uses 1 bit per photon in the end. And we're also we're fairly certain that we're not optimally using all of the information that we're gaining by using these Fourier qubits. We really think that we can push the security of this protocol further, but that is a kind of question for the math, and this is the hardest part. And so that's what we're working on right now with these Fourier qubits. So that's the end. I kind of went over some previous work, did some more background for us, and then went over the most recent work from our research group on free space quantum key distribution in high dimensions. And some main takeaways that I would like to leave with. Quantum key distribution is, as of right now, the only known way to perform provably secure communications that is safe from even a quantum computer. High-dimensional quantum key distribution allows for more information to be encoded in your channel for the same number of photons. So this is why you'd want to do it. And the really big one, free space, while it's called free space, is not free. And even though it is a necessary component of quantum key distribution networks for the future. And so the challenge of communicating with quantum signals through free space, quote unquote, is a problem that we definitely have to solve, and that's kind of what our group is working towards mostly. So thank you guys very much for listening to my talk and coming. I want to thank, of course, my group, the Structured Quantum Optics group, and everyone that I worked with, all of our collaborators at the NRC and colleagues, NextQT, Max Planck Institute, and Joint Center for Extreme Photonics. Thank you guys for listening. That's all I've got for you.
Thank you very much, Lukas. Well done, well done.
Thank you.
Nice videos and
thank you very much.
nice presentation. I did not know about the F-Qubits, and the adaptive optics is interesting too. The floor is open for questions. I see that Khaled has his hand. Go ahead, Khaled, if you wish to ask your question.
Hi, can you hear me okay?
Yeah, I hear you good.
Excellent. Fantastic presentation. I also grew up in Windsor, so that took my attention right away. So
nice.
That's good. Another Windsorite. Awesome.
Yeah.
So I find this to be very, very intriguing. At the same time, people have talked about something called classical entanglement. where you can sort of get the same type of correlations of the degrees of freedom of a beam. Um, and if we're looking at adaptive optics, is there some way, like for example, turbulence? My brother's a pilot, so he basically says turbulence affects the whole aircraft.
Mhm.
Like he was a snowbird, so when the snowbirds are flying, and there's thing that they all move at the same time. So that got me thinking is that if these degrees of freedom are quote unquote entangled or classically entangled, um, the disturbance would be upon them equally. Have you looked at that possibility? And what's your view on that?
So I don't actually know a lot about classical entanglement. I know it, in my experience, when people start talking about classical entanglement, there's always some really hardy debate that ends up going on about what does that actually mean. But I can tell you for sure that like the adaptive optics and the turbulence is going to affect classical beams almost exactly the same way. Because quantum, if you're sending single photons, what really changes is the statistics of the sending and the detection. So definitely, like classical beams, if you're just looking at sending classical beams, they'll be just as affected. But maybe it doesn't matter as much for classical beams because maybe you lose, half of the beam intensity, but you don't lose it all. Or even if you lose 90% of the beam intensity, you still have some. So while they will work the same, the turbulence is going to affect it the same. The consequences aren't necessarily going to be like as severe. Uh,
Alexei, do you want to ask your question?
Yeah, thank you. Thanks for the presentation. So unfortunately, I missed the first part. I have a few questions about the turbulence, that threshold criteria. So
yeah.
how did you choose that? Yeah, so that's the first one.
Yeah, so if I go, I just want to make sure that I know exactly what. So basically, this gray
Yeah.
area, right, is what you're asking?
Yep.
So we did that by. So we know that we wanted to do high dimensional quantum key distribution in this link. And so we did simulations where you can simulate the propagation of a beam and you can simulate the detection of the beam. And you can do simulations of turbulence. So we did like single phase plane approximations of turbulence, and we basically simulated the entire setup propagating through a 5.4 kilometer channel. And we kind of, I do have to say, arbitrarily chose we want to do 8 dimensions. We wanted to be a little pessimistic about when are we going to be able to do it. For the purposes of kind of talking about this, we wanted to really, we could have chosen we want to do it in 4 dimensions, but we kind of chose it because this is like a stretch goal that we would have. So we really would love to do 8-dimensional quantum key distribution, and that's our stretch goal. And so that's where we set it at.
Okay, I see. And another question. So you mentioned that you just to estimate your turbulence, so you basically took the data from Environment Canada observing site, right?
Yeah, for the weather data.
For the weather data, okay. And the rest?
So the weather data, and then we took. So we have this scintillometer device that's operating 24/7. So we took the previous we kind of picked a moment. Okay, we want to make a prediction, and we took that moment, the previous 12 hours of the turbulence data from our device, which we can get, of course, and then we used the previous 12 hours of the weather data that we got from the Meteorological Service Canada, and we tried to do it without our turbulence data, only using the Meteorological Service, but the network really wasn't performing good enough for our purposes at all.
I see. Okay. Thank you. I think I'll get back to you in person. So there are some more questions.
That would be wonderful. If you want to send me an email, I mean, I'd love to meet with you or anything.
Yep. Thank you.
By the way, if people in the audience wish to have a copy of the slides, they can either contact Lukas directly or through me, and we'll make sure you get a copy. Any other question in the audience? If not, we'll open the floor if there are, maybe not, but if there are people from this community wishing to really briefly present what they have been doing in this quantum communication world, present their research team or the company, the floor is yours. Last 2 times we didn't have anyone or too shy, but it's up to you. No one seemed to be interested, so thank you, Lukas, again. It was a nice presentation. We all learned something today.
Thank you. Thank you for the opportunity too. It's nice to get to talk about what I'm doing. So,
Yep. Good luck for your PhD.
thank you. Thank you. Okay, let's go. If anyone on Plex has any questions, just let me know, eh? Shoot me a service request or something, or a text, whatever. Okay.